All right, welcome to this explainer. Today, we're diving deep into exactly how modern game engines pull off those absolutely stunning visual feats using frame graphs and VMA, all without literally melting your GPU. I mean, have you ever been playing a massive open-world game, wildly spinning your camera around a bustling, highly detailed city, and noticed that not a single frame dropped? If you've ever wondered how today's engines manage to render millions of polygons, complex lighting, and ultra-realistic shadows in a fraction of a millisecond without just crashing your whole system, well, you are in the exact right place. We're going to explore the cutting-edge architecture that makes this all possible, taking us from the macro level of engine resource management all the way down to the micro level of painting flawless pixels.
So, here's our roadmap for today. First, the rendering complexity problem. 2, frame graphs and declarative rendering. 3, VMA, taming GPU memory. Then we'll pivot a bit to number 4, the shadow aliasing problem. Tackle 5, cascaded shadow maps. And finish the whole shebang with 6, smoothing shadows using PCF and VSMs. Basically, we're transitioning from chaotic macro engine architecture down to the absolute micro details of realistic rendering. Let's get into it.
Section 1. The rendering complexity problem, and how we go about teaming the beast. To really appreciate where we are today, we first have to understand the absolute nightmare the graphics programmers used to deal with.
This brilliant quote really hits the nail on the head regarding the early 2000s era of immediate mode rendering. Quote, immediate mode rendering, where every draw call was fired straight at the GPU like a shotgun blast. And that is exactly what it was. No real batching, no dependency tracking, no real concept of resource lifetimes. It was just throwing geometry at the wall and hoping the hardware can handle it. Now, it worked for a while, right? But as games grew more complex, the industry shifted to deferred rendering to handle dynamic lighting. But man, deferred rendering introduced a whole new kind of hell, massive synchronization bugs and memory leaks. Suddenly, developers had to manually track everything, when a texture was written, when it was read, whether the GPU had finished using it. It was honestly like building a precarious house of cards. Forget one single memory barrier and boom, undefined behavior, a crash game, and your entire Friday night of debugging is completely ruined.
Evolving from that brute force immediate mode in the early 2000s into the complex, incredibly fragile deferred rendering pipelines between 2004 and 2008 naturally led to a breaking point, and that breaking point finally led to declarative frame graphs, pioneered by engines like Frostbite around 2015. The industry collectively realized, hey, manually managing thousands of lines of fragile synchronization code, that's just no longer sustainable for modern AAA development. We desperately needed a system that could think for us, track dependencies automatically, and allow developers to actually focus on making the game look good.
Which brings us to Section 2, frame graphs, declarative rendering. What is truly revolutionary here is how frame graphs treat rendering like a smart compiler optimization problem, rather than a rigid, manual pipeline. Instead of micromanaging the GPU and telling it exactly how to do every little thing step by step, you just describe what you want the final frame to look like. Then, the engine figures out the most optimal way to get there.
At the very heart of this system is the DAG, or Directed Acyclic Graph. The absolutely crucial word there is acyclic, meaning passes never ever loop back on themselves. Think of it like a massive manufacturing assembly line. You can't send a car backward to get its engine installed after the doors are already welded shut, right? It has to flow in one direction, from producer to consumer. Because it's acyclic, the rendering system can automatically track resource lifetimes, seamlessly insert necessary sync barriers, and even call dead passes that don't actually contribute to the final image on screen. It is incredibly elegant because the math itself guarantees a valid execution order every single time.
So, this elegant concept compiles in 4 distinct steps. First up, it analyzes dependencies to see exactly what relies on what. Second, it performs a topological sort, often using what's known as Kahn's algorithm, which is just a classic, highly efficient method for sorting tasks that depend on one another, ensuring nothing happens out of order. Third, it calculates exactly how long each resource needs to live. And finally, it handles intelligent GPU memory allocation, carving out space only when transient resources actually need it, and immediately freeing it up when they don't. Moving right along to Section 3, VMA, taming GPU memory. Because look, even with a brilliant frame graph doing all that sorting, you still need a smart memory manager to handle the actual bytes. Enter the Vulkan Memory Allocator, or VMA. Vulkan is a ridiculously powerful modern graphics API for sure, but it doesn't hold your hand.
It forces developers to manage memory directly, which, if poorly executed, can lead to severe fragmentation and major performance bottlenecks.
We live in a multi-heap reality. Modern GPUs don't just have one giant pool of memory. Device local memory is incredibly fast for the GPU, but it is physically impossible for the CPU to write to directly because of the hardware architecture. It's memory baked right onto the graphics card itself, meant for pure rendering speed. Host visible memory is the exact opposite. If you aren't paying attention and accidentally dump your vertex buffers into host visible memory instead of device local, you are looking at a massive performance slowdown. We are talking 10 to 50 times slower. VMA abstracts all this anxiety away. It automatically selects the optimal memory type for your specific use case, totally freeing you from having to micromanage the hardware. The difference between the old manual way of managing those memory heaps and this new declarative setup is honestly staggering. To manually allocate a single shadow map, a developer might have to write over 60 lines of highly error-prone code, meticulously dealing with manual barriers and just agonizing over memory fragmentation. By combining VMA with a frame graph, that drops down to about 5 lines of declarative intent. The system just automatically handles layout transitions and smart suballocation under the hood. You tell it what you need and it just works.
And the results? By leveraging this suballocation and intelligent lifetime tracking, developers achieve a jaw-dropping 98% reduction in Vulkan memory allocations. Seriously, let that sink in for a moment. 98%. Not only does this massively reduce CPU overhead, but it also results in a 24% overall memory reduction. That is huge. That is 24% more memory you can now use for ultra-high-resolution textures, denser geometry, or richer environments, all while completely eliminating synchronization bugs. You are quite literally getting a faster, leaner, and safer engine just by shifting your architectural paradigm.
Okay, Section 4, the shadow aliasing problem. Now that we've tamed the macro architecture and memory management, let's take a breath, zoom in a bit, and look at a notoriously difficult micro-rendering task where all this tech really shines, rendering shadows.
So, how do we render high-quality shadows without completely tanking performance? This is the million-dollar question for graphics engineers. The primary enemy here is perspective aliasing. Imagine staring at a beautifully rendered, highly detailed castle in the distance, but the shadow of your character's sword right in front of you looks like a blocky 8-bit staircase of pixels.
Why does that happen?
Well, distant objects and close objects require vastly different shadow map resolutions. If you try to use one giant stretched-out shadow map for an entire vast open-world scene, it gets severely undersampled right near the player. You end up with these pixelated, shimmering edges that instantly break your immersion.
Section 5. Cascaded shadow maps. Because standard shadow maps fail so spectacularly in massive environments, the superhero solution to this perspective aliasing problem is cascaded shadow maps, commonly referred to as CSMs. This is absolutely the industry standard for handling shadows in large 3D environments today. CSMs solve perspective aliasing by breaking the camera's view down into multiple slices, or subfrustrums, along the z-axis. Think of it kind of like slicing a loaf of bread. The slices closest to you get the highest definition, maximum resolution shadow maps. The slices further away get lower resolution maps, simply because your eye can't tell the difference at that distance anyway. The engine calculates independent projections for each of these slices, generates separate shadow maps for each section, and finally renders the scene using the specific map that most closely matches the required resolution for that exact pixel.
But as we know, nothing in rendering comes for free. When partitioning those slices, developers have to weigh 2 different mathematical approaches. Fit to scene ensures a very stable projection. It wastes a little bit of resolution due to overlap, sure, but it significantly reduces visual artifacts. On the other hand, fit to cascade provides a much tighter resolution fit for the pixels, but the projection matrix constantly grows and shrinks as you look around. This can introduce really distracting visual artifacts, like shadows that seem to crawl or shimmer along the ground as the camera turns. And that's something gamers actively notice and heavily dislike. So it's a constant balancing act.
Section 6. Smoothing shadows, PCF and VSMs. To finish off our visual feast, we can't just leave those cascaded shadow maps with perfectly crisp, razor-sharp edges. Harsh, unnaturally sharp pixelated edges instantly remind the player they are looking at a computer simulation, right? In the real world, shadows are soft, they're diffused. We need to smooth out these hard edges using advanced filtering techniques.
We generally have 2 leading methods for doing this. First up is PCF, or percentage closer filtering. It filters the shadow edge based on depth subsamples, essentially calculating the percentage of a pixel that is in shadow. However, it requires a very strict depth bias. If you get that depth bias even slightly wrong, you get a dreaded effect called Peter panning, where the shadow literally detaches from the object, making it look like a character or building is magically floating in mid-air. On the flip side, we have VSMs, or variance shadow maps. VSMs perform a statistically driven filter using Chebyshev's inequality. Now don't worry, you don't need a math degree for this. In practice, it really just means using a statistical method to guess how much of a pixel is blocked from the light. This allows for incredibly smooth, realistic shadows, utilizing the GPU's native hardware filtering. The one downside, they can occasionally suffer from light bleeding, where two shadows overlap, making the center artificially bright. By bringing frame graphs, intelligent memory allocators, and advanced shadow algorithms together, modern rendering has truly become a symphony of automated optimization. We've successfully moved away from rigid rules and manual memory chores. So we want to leave you with this final, provocative thought. Now that we are no longer writing pipelines, but defining intent, what other complex systems in your own work could you completely revolutionize by changing how you think about the architecture? Thanks so much for joining me on this explainer, and keep building amazing things.